Okay, so what we have here is a mock-up of a mercury barometer. The way these things work, at least if I were to build one by hand, is I could take and pour mercury into a flask, a long, thin flask. And then if I had an additional cup of mercury, I could take that flask and turn it quickly upside down. And then some of the mercury would drain out of that flask, leaving an empty void up at the top. And it turns out that if I measure the height of the mercury column, I could actually determine the pressure of the air there at the bottom of the cylinder. But let's do that process kind of in reverse here. Let's say that I've got my mercury barometer all set up. And I know that here at the bottom, let's see, whoops, sorry, didn't have the pin activated yet. I know that right here at the, and again, I will get there eventually. I know that at the bottom, there, the part that circled the A and the B, that my atmospheric pressure, maybe I've determined it from some other source, maybe I pulled out the app on my phone, that this pressure is atmospheric pressure, and we'll just use atmospheric pressure at sea level. We'll say that's 1.013 times 10 to the 5th pascals. Okay, so that's our atmospheric pressure at sea level. Now up here at the top, right there, well, the flask is empty. There's nothing there, literally nothing there except for a negligible amount of mercury vapor. The pressure up top here, the pressure at the top, is effectively 0 pascals. Okay. All right, and the goal here is for us to figure out, well, what is this height of this, of this mercury column? All right, so this is another application of our equation that relates pressure at different depths of a fluid. There we go. P bottom is equal to P top plus rho GH. Now the pressure at the top is 0 pascals, so we'll just get rid of that. And then if we rearrange this equation and solve for H, we'll see that H is equal to P bottom over rho G. And we can fill in numbers here real quickly. 1.013 times 10 to the 5th pascals divided by our density of mercury, 13,560 kilograms per meter cubed, times G, 9.8 meters per second squared. And when we do this, we should get a value of, for H, of 0.762 meters. Meters of what? Well, meters of mercury. 0.762. Let's do something else. Let's convert that number from maybe meters to millimeters. That would be 762 millimeters of mercury. That number may be familiar depending on how much exposure you've had to pressure in the past, just listening to weather forecasts, whatever. You might have heard at some point in the past that atmospheric pressure, if we use a different kind of unit, is 760 millimeters of mercury. That's where this comes from, is this style of mercury barometer. Why did we get 762 instead of 760? Little variations in air pressure. All right, and that does it for this one. This actually was meant to be tacked on the last one, but I lost track of where I was. All right.